We'll start recording now sometime.
Good afternoon, one and all. Myself, Gautami Naidu, once again welcoming you to the third day of 3-day FDP program, Emerging Trends in Electronics and Computer Engineering. Now I request Dr. B. Ravichandra sir to introduce our speaker, Mr. Ayan Karmakar, Senior Scientist, Semiconductor Lab, Mohali.
Good morning all. Thank you, Gautami, for giving the opportunity to introduce Ayan Karmakar sir. Mr. Ayan Karmakar sir received the BTech degree Electronics and Communication from WBUT Kolkata in 2005. Later, he did his master's from NIT Durgapur. He joined Indian Space Research Organization ISRO as a scientist and subsequently posted to Semiconductor Laboratory SCL, Chandigarh. His research interests include design and development of LSCX and K-band passive micro-integrated circuits and antennas using silicon-based MIC and RF MEMS technology. His field of expertise and expanded in fabrication technology of various MEMS-based sensors and evolving the test strategies for the same. He engaged himself in high-frequency device modeling and development of passive devices for tetrahedge applications using silicon micromachining. He has more than 40 publications in reputed journals and conferences at various national and international levels. Recently, he has authored one technical book named Silicon RF Technology from Springer Publications, Singapore. He received multiple prestigious awards from Department of Space, Government of India for his active involvement and technical contributions in Rajabhasha Hindi. He has shown keen interest to build a strong communication link between academics and industry. In this context, he has delivered numerous lectures in the invited talk series of various institutes of national importance and webinars. He serves as a reviewer in reputed journals like IEEE Access, RF, MICIE, Springer, OQEL, IJET, etc. He is a fellow member of IETE India and life member of Indian Science Congress Association, ISSC, and Bangya Bigyan Parishad. Thank you. Thanks for giving the opportunity to introduce Mr. Ayan Karmakar. Thank you, sir.
Sir, thank you very much for this nice introduction. And I just want to thank to the whole organizing committee, especially Dr. Virendra Singh and HOD sir for inviting me and sharing this virtual podium to share my hands-on experience. So, am I audible?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So I'm really very much grateful to you as well as the whole organizing committee. So without any delay, I just want to start this talk. So regarding this talk, I just want to tell you one thing. This is my hands-on experience from the last 15 years. I just want to share with all of you. I know this subject is quite popular in nowadays, but I just treat this talk not as a simplex communication I will deliver and you people will listen. Rather, make it as an interactive session. Wherever you feel any doubt, you may raise your hand and ask any query to me. I will try my level best. So with these things, I just want to start my presentation. So the title of this talk is the MEMS, a promising technology for future generation wireless communication. I will start this particular talk with a very popular quote of Swami Vivekananda ji, one of the great sons of this soil. He told that every new concept has to pass through 3 stages: ridicule, opposition, and finally acceptance. This is true for the technical as well as the non-technical field. If you have that kind of potentiality and if you have some promising features, people will laugh at you initially. But if that particular technology or if that particular concept really has some tremendous potential, then afterwards people have to accept it. So that is applicable well for these MEMS, names, nanotechnology also. People don't accept it initially. CMOS And VLSI technology has a wide band features and really, I will say, other dominance. And in that particular field, if you talk about the nanotechnology or MEMS, this kind of things, then initially people will not accept it. But it has proven that it has also some potential and it has to be accepted. So in the subsequent slides, we will see how it can be proved. So this is a very brief outline of my presentation. We will go by the what are the activities going on in our semiconductor laboratory regarding this MEMS, and then we will go upon how the what are the basics of this MEMS technology also. Then we can see this semiconductor laboratory or SCL. Initially, it was a PSU. Then in 2005 only, it came under the administrative control of ISRO or Department of Space. And now on the year 2021 end only, it has come under the Ministry of Information Technology, so MIT. So it is the center, I would say, under a single umbrella, you will find everything. Like you will find the VLSI technology, you will find the MEMS, as well as you can flourish your optical or CCD things. And not only that, you can design your own circuit here. Finally, you can fabricate it, then you can test it, assemble it, and at the end of the day, you can make a whole system or a SoC concept with this particular foundry. So that is the beauty of this semiconductor laboratory. Under a single umbrella, you will get all the solutions. So in this particular presentation, I just want to mention one thing, that what is MEMS? Before initiating the actual things, you should know that what is MEMS. MEMS, it is the acronym of micro electromechanical system. From the name itself, it is very clear that it is the amalgamation of multidisciplinary subject. That means electrical is there, electronics is there, mechanical is there, and finally the system engineering also is there. This term has been coined in the late 70s or in 80s. In the Japan, people used to call it as a micro machining or micro machine. And in the Europe, it is known as a microsystem. And few people also call it as a 3Ms. For what? For miniaturization, multiplicity, and microelectronic finally. Now, we just want to realize what will be the shape, what will be the dimension of the device, how it will looks like. So for that resemblance, I have put few pictures here. That is, it is just like our RBC or WBC, white blood corpuscle or red blood corpuscle in our blood, or just like a human hair. So this will be the dimension of the order of the device after fabricating these MEMS devices. And for a broader range, you can look at this particular slide also. This particular slide tells you what will be the dimension, what will be the scale of the device. Now, in a broader way, you can say if the dimension of the device is in the range of millimeter to micron, then it is known as a MEMS technology. And if it falls below 1 micron, then it is known as a NEMS or nano electrical mechanical system. So at this juncture, we can recall a very popular quote of Dr. Feynman: there was plenty of spaces at the bottom. So that is true for this MEMS technology, nanotechnology, NEMS technology, all these things. So you have a huge opportunity for flourishing your device, flourishing your development, system engineering, everything. So before going to this thing, we will look at this. What are the basic components of this particular MEMS technology? We will look this particular figure. It's a figure depicting it. This particular technology consists of basically 4 basic building blocks, that is sensors, microelectronics or VLSI, or we can say it as a ASIC, application specific integrated circuit, then actuators or some microstructures. Obviously, power supply is required for the signal transduction and processing units and all other circuits. Now, if somebody calls you, somebody asks you that what are the different applications of this MEMS technology, or in other words, where can we use this particular MEMS technology? The answer is everywhere of human life. So according to the application of this particular technology, this particular MEMS can be classified broadly into several categories. Just like if it is used only for RF or microwave engineering, then it is known as a microwave MEMS or RF MEMS. If it is used for biomedical engineering, then it is called bio MEMS. And if it is extensively used for the optical engineering, then it is known as a optical MEMS. And not only for that, for the physical sensing, just like pressure sensor, then temperature, RH sensor, hygrometer, all these things can also be done with this physical MEMS category. So look at this particular slide. This particular slide gives you a very short glimpse of the devices which can be fabricated, which can be developed with the help of this MEMS technology. There is a huge difference and a wide band, I should say. Just like if you touch upon this RF, you can build your capacitor, inductor, then switches, antenna, phased array antenna, phase shifter, the whole system. If you talk about these meters, then you can make micrometers, heaters also. Like that only, you can make level sensor, pressure sensor. If you enter into the navigation system, you can make accelerometers, then gyroscope, all these things. So it has a huge or wide area. And if people ask you about what are the inline process technology of this MEMS, so basically there are 4 process technologies are there: bulk micromachining, surface micromachining, electroplating, and the wafer bonding process. And the bulk micromachining process will tell you about if the bulk of the material or the bulk of the substrate is removed either by chemical means or by physiochemical reactions, then it is known as a bulk micromachining. Just for an example, you can take, with the help of KOH, 40% potassium hydroxide solution at 80 degrees centigrade, this KOH is used as a strong agent of silicon. So with the help of this KOH, you can make cavity like this, and this angle will tell you about around 54.7 degree, and this is the slant angle you can make with the help of this KOH. You can make a straight one also. Then you have to go to move to some other etching technique that is known as a high aspect ratio etching or the deep reactive ion etching. So with the help of this bulk micromachining, we have understood that we can remove the bulk of the material underneath some important structure. So surface micromachining is the another second important process of this MEMS technology, by which you can make a free hanging structures out of your microstructures. So which is completely impossible in case of your standard VLSI or CMOS technology. So that is the beauty of this MEMS technology. You can make free hanging structures like cantilever, like free hanging switches. You can make a free hanging inductors also, lots of devices, and you can make this particular cantilever usable for your bio application, for your RF application, for sensing application, anywhere. It depends upon you where you want to use. And then coming to this wafer bonding technology. Wafer bonding is another unique process which is present only in case of MEMS technology, unlike your CMOS or traditional microfabrication technology. With the help of this particular process, we can bond multiple wafers, just like, for example, whatever wafers we are using in our 6-inch process or 6-inch technology, we normally use as a 575 micron to 625 micron. This is the band of the thickness of the silicon wafer. But suppose if some RF engineer comes to you and if he wants a silicon circuit where silicon thickness would be 1.5 millimeter, then what you will do? You have to make bond of two silicon wafers with the help of this wafer bonding techniques. So that you can have this kind of 1.5 millimeter, like you can make cavity or anything structures like that. So there are two kinds of bonding available here. Either it is known as the anodic bonding or it is known as the eutectic bonding. There are other bonding techniques are also there, but that is not so much popular. People call it as a dirty process, just like glass-free bonding, because lots of contaminations will be there, lots of particles will be generated, which may hamper your circuits very badly. So people have to discard. So there are basically two major processes of bonding. So one is known as anodic bonding, another is known as eutectic bonding. From the name itself, it is clear that anodic bonding will involve anodic process. That means where anions or cations will move. So here we normally use sodium-rich glass wafers to bond with the silicon wafers to make your cavity sealed. Sometimes, whatever I have shown in the bulk micromachining slides already, suppose if it is a cavity has been formed and I want to make that cavity as a reference vacuum level. So make that vacuum level, I have to seal that particular cavity. To force that sealing purpose, I have to seal with some glass wafers with the silicon wafers. So that makes a recall of this anodic bonding. Whether in case of eutectic bonding with the help of a very, very thin sandwich gold layer, you can make a good bonding between silicon to silicon with the sandwich layer of gold. And at the 363 degree centigrade temperature, it will happen. So here is a comparative study of these two bonding techniques. You can have a look on this particular technology. And then coming to this electroplating process also. Coming to this electroplating process, you can think about whatever the microfabrication technology is there, that microfabrication technology will allow you only up to 1 micron maximum metal thickness. You can make a stack of the thickness, but it can go up to 2 micron or maximum 3 micron by breaking your vacuum in the process chambers. But if you are an RF engineer and if you are considering the skin depth kind of concept, and if you are demanding from a process engineer that I need a 25 to 30 micron metallization thickness, then they cannot provide you. Then you have to come to this particular technology, which will give you very easily 20 to 30 micron, even it can go beyond that, this electrolytic process. So this is also one of the unique process, little bit dirty process there. You have to make that wafer cleaning after so much post-processing, and cleaning techniques are also there. Now coming to that, why this particular micromachining, bulk micromachining technology is there and how it is useful for RF engineer. You can say this particular figures will tell you this is the ideal figure, where you can say this was your microstrip line structures, but this microstrip line structures, I make it as a air gap beneath this thing. So particularly this, say this is one live line, or this is one ear antenna. So this ear antenna is looking to this thing that its effective permittivity of the substrate has been decreased and it has been tended towards the air. It is very, very nearly equal to 1. So there are three kinds of losses, as you know. One is known as the ohmic loss, another is dielectric loss, finally is the radiation loss. So ohmic loss you cannot alter too much because you have a very limited choice of metal in any foundry. So either you have aluminum or you have platinum, or very, very limited choice in a particular foundry. So you cannot go beyond that. So talking to that radiation level, you can take one in the design itself. And if you are an antenna engineer, then you need that radiation at a particular direction. But only one culprit is there at that juncture, that is the dielectric or the substrate loss, which will dominate your circuit performance. And for getting that thing, you have to think, how can I reduce my substrate or dielectric loss? So this is the one way to reduce your substrate or the dielectric loss. So that's why this particular technology, bulk micromachining, the MEMS technology, has become so much popular for making the miniaturized antenna in nowadays. So this is the practical thing. This was the ideal thing, and this is the practical thing where you can see this particular antenna is looking after a big column of air, and ultimately at this particular point, it is getting that my effective permittivity of the substrate is nearly equal to 1. So that's why it will incur very less kind of loss. Surface wave, leaky wave, all these kind of losses have been eliminated. Obviously, higher radiation efficiency will get, less dispersion, higher bandwidth, and obviously higher sensitivity to change in case of epsilon or effective permittivity. And if you are an RF engineer, you know that there is one hexagon is there. So that hexagon determines what are the bottlenecks, what are the optimization techniques in your designing. So that is interdisciplinary knowledge, and you have to think about how can I minimize my noise, how can I minimize my power budget calculation, link budget calculation, all these things. So that is applicable here also. You have to think about your linearity, then frequency response, obviously power budget and noise reduction technique. So that is applicable for MEMS also. And if you are thinking about in nowadays electronic circuitry, you will find that everywhere for the communication, we are going to use knowingly or unknowingly various micro machined miniaturized antennas, and those are nothing but planar antennas. And these planar antennas have various advantages, you know, but it has also some issues also. It's very low gain, low directivity will get, and low radiation efficiency, and all these issues can be resolved effectively with the help of this MEMS technology. So that is the beauty of this particular MEMS technology, where you can get freed of that kind of problem. From this particular slide, you can understand how this can be mathematically or analytically resolved. And look at this particular two pictures, where it is very much clear how that field propagation, electric field orientation will also get changed. And finally, at the end of the day, we are going to reduce the substrate or the dielectric losses, and we can reduce the leaky waves, surface waves, all these problems also. So that's why this process are very much popular, not only for this RF or microwave engineering, even it is applied enormously for this millimeter wave technology, for the 5G, 6G, for this future wireless communications also. And if you are talking for this future wireless communication, one of the main challenge of everybody wants that I want a multi-band and circuit, but I need a very, very short profile, a very, very short footprint of that particular circuitry should be there. So for that thing, you have to make some vertical integration, just like this figure. So you can make different wafers ready for different circuitry, like one wafer for your active circuitry, amplifier will be there, another wafer will be for your divider circuitry, another wafer will be for your antenna circuitry. So after making all these circuitries separately, then you can make a vertical integration out of that thing, and so that ultimately at the end of the day you will get a small package system on package concept with the aid of this vertical integration, and with the help of this wafer bonding techniques, bulk micromachining techniques, and so that you can have this kind of compact circuitry at millimeter wave technology also. Dr. G.M. Revis has reported in his book also up to 94 gigahertz anti-collision automobile radar can, that kind of circuitry also he has reported. This concept can be used effectively there also. And if this is applicable for making a complicated and enhanced version of the antenna, just like aperture coupled antenna. You know, this aperture coupled antenna is one of the promising antenna in the microfabrication or miniaturized antenna technology, but it has some demerits also. It's very, very complicated to fabricate. So it is hardly impossible, you can say, using the standard PCB technology, but it is very, very useful or very easy to make with the help of this MEMS technology. You can make a perfect alignment because you are using basically lithography tools, standards lithography tools used for this standard microfabrication technology in case of MEMS technology. So that's why it will be aligned very perfectly. It will be aligned, and not only that, you see, these are the three different wafers stacks are there. By the end of the day, you will bond this particular wafer stacks to make this kind of arrangement, and ultimately your antenna can be excited with the aid of this kind of feeding technique, and you can make a beautiful slot here which will be aligned to make the proper leakage of your excitation waves. And this, there is a misalignment chance in case of your PCB, but here there is a misalignment chance is very, very less. And if you were talking about this array technology, you know, this array technology is required to have a very, very wide band, very wide gain kind of thing, but it has also some demerits. You will excite this array with with the aid of some feeding technology, with the aid of some feeding network, and that feeding network at the higher frequency, it will be a source of your spurious radiation. Or in other words, I can say that feeding network itself will act as an unexpected antenna. So to stop that radiation, that is not required by the designer. So to stop that radiation, you have to adopt some strategy. So that strategy is that you can make multiple blocks, multiple hollow blocks, just like bulk micromachining, and so that this field coupling, the field responsible for the mutual coupling, got cancelled or got diminished, so that it cannot interact with each other with that cross coupling kind of things. Ultimately, your effective radiation efficiency will be higher. So this has been proved up to 110 gigahertz. And if you are thinking about this high aspect ratio filter, just like the filter is nothing but a cavity, you can think about it just like your room, and that particular cavity quality factor is directly proportional to the volume of that room or volume of that cavity. So you can enhance the height of that particular filter or height of that particular cavity, but you have the limitations of the wafer thickness normally, but you can get rid of that wafer thickness limitation with the help of that wafer bonding technique, or in other words, with the help of this MEMS or micromachining techniques, so that you can have a thick, or should say you can have a high Q filters with the help of this micromachining technology, which is not possible for normal standard fabrication or microfabrication technology. And if you are thinking about a system just like a phased array system is nothing but it is used in our common daily life. Suppose if I am giving this particular talk to a large audience in this particular webinar, and few audience don't want to listen me. So though they are look at their particular laptops, screen, but they are not listening because their mind is not tuned to this particular talk, or they may be of off field, so they don't like. So that is the concept of the phased array antenna. If I want to direct, or if I want to orient the particular antenna radiation in a particular desired field, so that is the particular direction or the orientation where I want to propagate my signal from the source to the receiver. So others will be masked at that time. So that is the concept of the phased array systems. And the phased array system, you have to make some arrangement of the switches so that others will be masked off and only rest of the portion or your desired portion will be on, so that your antenna will be responsible to communicate with the source and the receiver. And there are basically two scanning techniques. One is known as the mechanical way, another is the electronic way. So mechanical way was the earlier thing, traditional thing. It's a bulky in nature, wear and tear problems will be obviously there. So to get rid of this bulky wear and tear problems, and obviously there is a failure chance to go make a tiny, very compact thing. So ESA has come. This is the electronic scanning array where you will use your phased array antenna, and this phased array antenna ultimately consists of lots of phase shifter, your antenna, switches, and all these things. So it can come down from your MEMS things. So how this scanning is done, this is the way I am showing here. Suppose at the T0 instant, this is the transmitter which want to talk to this particular receiver. The rest of the receivers are not working, and in say T1 an instant, it is talking with say mobile 2, and at that time M1 and M3 are not communicating. He is not communicating with the M1 M3. So this is the way it can move from one receiver to another receiver. So this is known as the scanning. So this scanning can be done either 180 degree, or it can be done on a full 360 degree also. So these are the techniques which we normally demands, that these are the existing technology like ferrite solid state technology. And this is the comparison table you will find from this particular reference of Gabriel Reby's book, and it's a very popular book. You can say this is a Bible of this MEMS technology. He has reported that how this MEMS technology is superior. It has some promising technology with respect to this existing ferrite. This is a bulky, obviously, and it will it's a very much power hungry devices are there. Obviously it's a bulky, power hungry, but it's obviously it's a very good thing. So it can replace slowly all these things with the help of these reported results. Look at this particular slide very carefully. From this particular slide, we can see that this is not only true for the lower band technology, but also it's true up to W band, up to 94 gigahertz to 110 gigahertz. This kind of band also it can and be supported with this MEMS technology. So that is the beauty, that is the potential of this technology. So nowadays in SCL, these are the technology available. This is the gallium arsenide technology. It's a booming up technology. It's not fully ready at this moment. Silicon technology is available. So if somebody is planning to make some monolithic integration with the CMOS technology, so it's easy, or I should say it's viable to get it here. And the practical application of this phased array antenna, if somebody wants that how this is possible, what are the different practical applications of this phased array antenna in space? I think this we have read in the newspaper also. The Messenger spacecraft was a space probe mission to the planet Mercury in the year 2015. It was completed, and basically it consists of X band, and it consists of 26 radiating elements. So this is the practical application of the phased array antenna system, which is used for this instrumentation in the space technology also. Now, if we are thinking about how my silicon can be used in the RF application, which is known as the silicon RF technology, and how this is used everywhere in our daily life. So that is nothing but a SoC or system on chip concept. So that's why there is one proverb people used to call the yesterday chip is now today's functional law. That means how the miniaturization is getting happen. So there is a paradigm shift. That's why system on board to the system on chip. This kind of paradigm shift, miniaturization is going to happen. And this is the equivalent technology. You can say this particular circuit will tell you about the, if you use your silicon for RF technology or for the high frequency application, just like a transmission line, this particular silicon is also can be modeled. And this is nothing but a high resistive silicon. The normal standard silicon cannot be used effectively for this high frequency application. Rather, you have to use HRS or the high resistive substrate silicon, which has some property like it has uniform resistivity throughout the thickness of the wafer. It has the acceptable radial and axial resistivity gradients, and it has a stable resistivity throughout the device processing. That is the one of the beautiful feature it has. And if you plot this particular substrate loss, you will find this substrate loss is nothing but a function of frequency and resistivity. So that's why this silicon itself will support two kinds of mode. One is slow wave mode, another is quasi-TEM mode. And if we want to use still for the lower frequency, the standard CMOS grade silicons, you have to go by the 7 process. 7, these are the standard process you have to go. So one is either you have to build some thick oxide layer, or you have to go by this thick nitride, or you have to go by the stack of the oxide nitride. It can be altered, or you have to make some make of this thick oxide layer. You can go for this polyimide layer also. So what are the promising features? Why I should go for this RF MEMS, or why I should go for this MEMS technology to have some RF circuitry? So worldwide, globally, there are basically two techniques are there. One is known as bottom to top approach, another is known as top to bottom approach. So bottom to top approach, normal maximum people used to follow. We in our SCL also follow this. So this is known as the bottom to top approach. First, we will start with the small circuitry, basic building blocks. Then you will go by the little bit higher level. Then finally you have to integrate at your system. So this is the example of a simple transceiver circuitry where this highlighted portion are showing that these are the potential fields where MEMS can enter. Okay, so whatever the circuitry is there, whatever the technology is there, you have to go by these 3 basic techniques. First, you have to model it, you have to characterize, and finally you can you will be able to develop your circuitry. So silicon is a substrate which has a tremendous potential. It can go up to terahertz also. So terahertz is a technology, or I should say there is a gap of the technology in the still now a few years nobody was talking about this terahertz, but it is not unknown. It was known, and for that particular technology, we were not ready to use that particular technology. Why? Because if you want to use that particular technology, you have to get ready with your amplifier, with your active circuitry, with your full communication link also. But that is not ready for this 100 gigahertz to that 1000 gigahertz application. So for that huge wideband application, your circuitry was not ready. But now people are thinking that why not to use this terahertz, because it has a tremendous potential for your surveillance purpose, for imaging purpose, medical imaging. So long back in 1890s, Professor J.C. Bosch has got the foundation. So long back in 1890s only, Professor Jesse Bose has shown that this promising features of this terahertz technology, that it has some tremendous huge bandwidth. If you are able to use only 1 or 2% of this particular band, you will be ready enough to send your data from here to there with a very huge speed in terabyte per second. So only one bottleneck of these technologies that already I have told you. Another is that water or the absorption. So absorption with the hydroxyl molecule is really very bad at this particular technology. So you will not go for the long haul communication, rather you will go for this short distance communication, where you can and effectively use for this terahertz technology for either for surveillance or imaging or for or data transferring within the lab or within that building itself. So now you can see this particular slide will tell you about what are the different things which you can make with this terahertz silicon, and using this silicon foundry you can make your terahertz things. Lots of transmission line things you can make with this help of this silicon micro machining, and this is the technology, MEMS technology, which will make you knowingly or unknowingly will make you capable to use your circuitry ready for this terahertz application. You make like hybrid kind of circuit, you can make power divider, then you can make OMT. So these all are the circuit elements for used for the antenna or the whole transceiver chain. So you can get all the reference with this very popular paper of Dr. Chattopadhyay. He is in NASA. So in this particular paper itself, in all of his work, he is showing how this particular silicon technology can be used for this terahertz domain. And normally, he has shown even up to 25 wafers bonding together. I have read that paper 2-3 times. So this is the, and I was lucky enough to meet him in Bangalore in one international conference. So I interacted with him, how that Professor Chattopadhyay and his team in NASA are doing in the JPL laboratory, how these things are going on. So this is also possible to make in our India also, but I will say that we are not opportunistic enough to have this kind of circuitry, because if you want to make this kind of circuitry, you have a very dedicated team, not only for that, for the measurement and the test and characterization also, you should have that kind of 110 gigahertz, and beyond that VNA is there, flange is there. So all that setup are really very, very costly. So that is the bottleneck of the technology. And if you are thinking about this inductor, it's a very simple thing, but this inductor, as per in our bookish knowledge, we have already studied that this is the circuit element which we cannot make in the VLSI technology earlier, but now MEMS has come with the technology. This is also possible for the micro fabrication, but beauty of this inductor in the MEMS technology, look at this particular figure. This here, this inductor is hanging just like a crab, a spider. Okay, so this Q factor has got enhanced several times. It can go up to 100 with the small inductor. So that is not possible with the CMOS technology. And if you are thinking about a simple switching element, so that is also possible with the help of this MEMS, whether it's a capacitive switch, whether it's a series, shunt, any kind of switch also you can make. And this is the very basic building block which is required to make your antenna ready for phase shifter application or phased array antenna kind of things, or various reconfigurable circuit also. Just like reconfigurable antenna, with the MEMS you can say this reconfigurability or the I should say this kind of alteration can be done either in frequency domain or in polarization, or it may be of a combination of these things, pattern also. So there, whether particular switching elements will be on or off. Say some switch matrix will be there, and that in that particular matrix, whether that which switch has to be put on and off, there will be some ASIC which will consider at some instant which has to be on and off. And in that particular fashion, you can make your reconfigurable antenna with the MEMS technology. And not only for that, Vector also you can with this MEMS technology. And this is the very popular comparison table where you can see what are the different advantages of your MEMS Vector in comparison with the CMOS standard Vectors. And it is applicable for our 4G, 5G, and beyond that also. That is the beauty of this thing. So with this thing, just want to end up my presentation. These are the reference of my presentation. Thank you.
Sir. Yes, sir.
Yes.
It's like a quite refreshment to ma'am, sir. One question someone has posted in the group, sir. How can we differentiate between NAMs and MEMS?
Mainly we can
quantitatively or qualitatively, how we do differentiation?
Okay. Mainly their differentiation comes from the device dimension. If the device dimension means the smaller critical dimension, मतलब एक जो सबसे जो lowest वाला जो dimension है, if that comes below 1 micron, then you can name it as a NAMs. Otherwise, it's a MEMS.
Yes, sir.
So there is a very fine boundary basically.
Yes, sir. And my question is, sir, what about the simulation of RF MEM devices? Sir? How do you simulate, and how much you are reliable, or how much you consider simulation of these devices?
So for that simulation, normally suppose if you are doing this kind of simulation, you have to go by these 2-3 kinds of simulations basically. Why should I say? Because suppose some structure, if you are using for your RF or microwave kind of things, obviously that structure has some mechanical assembly is also there, and some mechanical engineering is also there. So for that thing, some distinct tool is there. ANSYS you can use Coventor also. There are co-solve simulation you can use. Another thing is that, okay, if you are passed through that mechanical things, then you have to go through that actual intended thing of your RF. Say, as for example, it's a switch. So at the on and the off, how it will behave. So that portion you have to consider in either ANSYS, HFSS, or in some standards, AWR, or other simulation, 3D simulation. Basically, we do FEM simulation kind of thing. Then the third one is that, suppose if you are through with this, all these 2 previous, whatever I have told, then you have to go by this circuit simulation also. Suppose any circuitry, say as for switch you have taken or antenna you have taken, so that particular circuitry obviously has some equivalent electrical model, and that equivalent model you have to also simulate. That means RLC kind of consisting that kind of simulation you have to do it with the standard circuit simulator, just like Agilent circuit simulator, ADS, or you can go for normal CST microwave studio also, 3D as well as then circuit simulation. This or AWR also you can go.
Yes, sir. One more question, sir. If you are able to see in the chat box, sir.
Is there any effect of radiation from antenna in the multi-layer MEMS?
Yes, I am able to see the chat box. Differentiate MEMS and NEMS. Yes. Is there any effect of radiation from antenna in the multi-layer MEMS chips used in the? Yes, Of course, there is a radiation effect of the antenna, and that has to be taken care by the designer itself, because as just now I have told you that ANSYS, HFSS, so it is there. So in that particular things, there is one option, radiation box is there. So radiation box designer has to put in such a way, generally it has to be taken with the center frequency, then lambda g by 4 guided wavelength, and 1/4 of that guided wavelength. You have to make some boxes, and then you have to see how the fields are there, whether it is leaking from somewhere else or not. So that has to be taken care. It's a very good question, and we have to consider all these things. How can I improve the pull-in voltage in RF MEMS switch? Yes, pull-in voltage in RF MEMS switch, there are so many ways. If you are thinking about the basic design kind of things, you have must remember what are the VP related to K, then you have to G also, that means air gap height. So all this kind of thing depends upon what are the choices available at your hand. Like if you are going to fabricate your things in India in say X foundry, then you have some limited because they will provide you I cannot go below 2 micron gap. But if you are moving to US and they are telling us select according to the your constraints basically, then you have to come to the K spring constant. The spring constant, it will depends upon your design. You can make crab like structure, you can make simple fixed beam. So from that crab like structure to fixed beam, obviously K will change, and obviously that K will affect your pull-in directly. And these are the ways, and then you have to consider the what are the different dielectrics are available with you, because you are going to use some dielectric, very thin dielectric layer, though in the above the bottom electrode. Then so that what kind of thin, how much thin they can provide you, that foundry can provide you, that also you have to think about. One question is that VLSI and MEMS, how can we differentiate between VLSI and MEMS technology? There are lots of differences. One major difference you can say, basically MEMS is nothing but they are using all the VLSI steps and all the VLSI machines also, but you can differentiate this particular MEMS technology with the help of these 4 unique processes, whatever I have told. Bulk micromachining processes, surface micromachining, then wafer bonding and electroplating. So these 4 processes, and with the help of these 4 processes, you can make your structures hanging, you can make cavity, you can make thicker wafers, you can make thicker metal. So that is not possible in case of your standard VLSI or standard microfabrication technology. So that is the main important thing. How can you improve the reliability of a switch? The reliability of the switch can be improved in several ways. This question is I should say it's a subjective question. Okay, so in a single line, I cannot answer. So reliability of the switch can be improved in several ways, just like you have to, if you want to make it as a reliable for say your space grade, then you have to consider each and every step. What are the different material I am using? Suppose the free hanging structure which will come up and down, that means the membrane structure. So ductility of that particular structure you have to see. Then what will be the particular thickness, then how much cycle it can and go. And not only that, suppose if you are through with all of the things, then you have to think about, finally I have to use this particular circuit for some end application, so I have to obviously package. So that package also plays an important role in determining the reliability. So that reliability not only depends upon your design, but also depends upon fabrication process, packaging, And if you are thinking that I will make a reliable device in a single shot, it's not possible. You have to go by iterations only. But, everybody has to learn from the failures. So I will go by one, how that can be. Okay, then. Okay, that's all from the question. If any question.
Okay, sir. It's very interactive section, sir. Look,
Thank you.
our audience are very much interested in antenna. So I request
Okay.
Dr. B.C. Prasad, sir, to give thanks.
Namaste,
Close the
Ji.
session.
Thank you.
Yes, sir. It's wonderful, sir.
Thank
You
you,
covered
sir.
you covered my topic also, my research topic completely.
Thank you, sir.
I've used pin diodes, sir, for reconfigurability.
Okay.
Pin
Pin
diodes
diode.
for LTE, WLAN, Wi-Fi, satellite communication application.
Okay, sir. Nice.
Incorporating pin diode, little bit easy, I think, than this MEMS switches
Yes.
in antenna structures.
Yes, sir.
So what may be the expected change if you use different kinds of MEMS switches rather than?
So different changes means you will see the changes in case of say pull-in voltage extra you have to use, but you will face one thing is that if you are using pin diode and then if you are using this MEMS, you will get very low kind of losses in case of MEMS, because insertion loss will be very less. Even you will find less than 0.5 dB maximum, I am telling. And if you are using some commercially available MEMS switch, you will get 0.1, 0.2 dB also they are assuring, but costly little bit. So if you are thinking about that kind of highly efficient and antenna is there and where we should use, then I will recommend that MEMS is quite superior.
Faster switches.
Yes, faster switching also. And linearity point of view.
How many in an antenna structure? So what is the maximum possible number of switches we can incorporate? Like if you consider PN diode, so incorporated more than 5, 6, 7, 8 diodes also.
So that kind of limitation is not there because you can fabricate the whole antenna as well as that switch at a single stretch. So that is the beauty, because in the batch processing you can process the whole antenna as well as your MEMS switches. You can plan for that antenna fabrication at the silicon.
Different locations also we can.
Yes, different locations also, sir. You can, and that location you will find from your simulation.
Yes. Doing parametric analysis, we can find out
from the parametric analysis. Yes, sir. And current distribution also you will see.
Yes.
Yes, sir.
Thank you very much, sir.
Thank you, sir.
Session. It's a very wonderful session.
Thank you very much
interactive.
for inviting me.
Now we are glad, sir. We are glad, sir. We are very glad, sir.
Thank you.
Okay.
With all of
Thank you. Thank you, sir. Namaskar, sir.
Sir. I request
sir,
the members to switch on the video once. Switch on your video once.
Switch on.
I request all the members to switch on the video once. I request all the participants, the members to switch on the video once. Thank you, one and all. Sir, thank you very much, ING. Thank you for your session, wonderful session.
Sir, Professor Jafar, sir, have joined, sir.
Welcome, sir. Jafar Ali Khan, sir. Now, Gautami, proceed to the next session.
Now I request Mr. Sheikh Sultan sir to introduce our speaker, Professor Jafar Ali Khan Muhammad, IIT Hyderabad.
Good afternoon, everyone. Myself, Sultan, Assistant Professor, Department of ECE, NSRIT. With immense pleasure, I invite Professor Zafar Ali Khan Muhammad from Department of Electrical Engineering, IIT Hyderabad. He did his BE, Electronics and Communication Engineering from Osmania University, Hyderabad, and MTech in Communication and Radar Engineering from IIT Delhi, Department of Electrical Engineering in 1998. Professor Zafar Ali Khan Muhammad has done his PhD from IISc Bangalore, Department of Electrical and Communication Engineering, 2003. His research areas are coding and signal processing for 6G, theory of wireless communication, MIMO decoding, commensal radar, CPS security, dynamic spectrum allocation. He was honorary fellow member in University of Wisconsin-Madison in May-June 2008 and visiting professor in UC Irvine, University of Southampton in 2014 and 15 for 2 months respectively. His awards and recognitions: A.K. Sinha Award for the highest CGPA in IIT Delhi in the year 1998, INAE, Indian National Academy for Engineers Young Engineer Award in the year 2006. Space-time codes developed as a part of PhD were adopted by IEEE 802.16 2005 standard for 3 transmit antennas. IEEE ComSoc SP chapter appreciation award for the year 2013 to 14. Visvesvaraya Young Faculty Research Fellowship in the year 2015 to 17. And his projects: project manager in M2 Smart project funded by JICA, Japan for the period of 2017 to 22. Principal investigator in TVWS trials, project funded by Department of Information and Technology, India for the period 2010 to 2013. Principal investigator in cyber physical systems, project funded by Department of Information and Technology, India for the period 2011 to 16. Co-investigator in Cognitive Radio project funded by Department of Science and Technology under IUATC project, India, period 2012 October to June 2015. Thank you, sir. Over to Zafar Khan, sir.
Welcome, sir. Professor Zafar Ali Khan Mohammad Sahab. Istiqbal hai, sir, aapka, please.
Thank you, thanks a lot for inviting me, Dr. I congratulate all the organizers of this conference. Will you hear me clearly?
Yes, sir. Yes, sir. Audible.
Yes, sir. Yes, sir. Audible, sir.
Yeah. If I open the video, the voice is breaking. So if you want, I try it for some time. But if it's not working, I allow me. Okay. See, and the slides are visible.
Slides are visible.
Yes, sir. Yes.
Your little bit voice is
Visible, sir. Now clear, sir.
Yes.
And voice is clear. Yes. So what we are going to speak today is what we have been experiencing for the past few years in the area of signal processing. We have been working. And so,
sir, excuse me, sir, your voice is not clear, sir.
And Dr. Akib, who is at Qualcomm, he's also
सर थोड़ा ब्रेक हो रहा है सर आपका वॉइस.
And I probably
switch off the
video. Let me see if that works for you.
I request all the members to switch off the video.
Yeah. Yes. So today's topic is signal processing for next generation network, last 6 to 7 years. Is the voice clear now?
Yes, sir. Now clear, sir.
And this is a joint with and Dr. Aki Patel, who is a collaborator and also working at Qualcomm Research Lab. Okay. Today we'll just go through L processing. We are for next generation networks. We are concentrating on signal processing for massive MIMO and RIS systems. And the reason I this is because it will be apparent in the few slides. But as always is happening, it has not been able to deliver what it promised. So there is already a lot of us on improving the massive MIMO technology and or 5G, and that is what is called as RIS or reconfigurable intelligent systems. Okay, so we'll see that in a few moments. And there are a lot of mathematics also involved, but I'll try to give you the list of what I am working on. Are you with me?
Yes, sir. A little bit disturbance, but yes.
Okay. Okay, so first we'll straight away go into the these states are quite common these days. So because of the massive increase in data rates that is projected and because of a lot of devices that keep getting connected, so the requirement of data rate is exploding. It is not exponential, it is more than exponential. You can curve it is exponential. But those bandwidths, your data rates, you need spectral efficiency basically depends on the technology that is being used. So every G typically adds between 10 to 100. So from starting with kilohertz, we went to megahertz, speaking of gigahertz, right? So spectral efficiency typically increases by a factor of 10 per G. But the important point, so the extra throughput that we want has to come from bandwidth. So unfortunately, bandwidth is a prime commodity. In fact, it is the most precious natural resource available. Right? It is more precious now than gold. It is more precious now than land. It is more precious than oil. You remember the 2G auctions? There was big buzz at that time. Yes. Anybody? Anybody remember the price of 2G auctions? 2G, 3G? By the way, 5G auctions happened just last month. Is anybody aware of that? Because
Yes, sir. We heard the news, but statistics are not with us, sir.
No, I want response from the audience also. Right. So there's a lot of buzz for 2G because at that time the price that went for 2G auction was huge, thousands of crores, right? The scam itself was of 2,000 crores something. Do you remember that?
Yes, sir.
Yes, sir. Yes, sir.
Yeah. But so remember that bandwidth is the most precious natural resource these days. Okay, and so most of the countries, if you control the natural resource, you control the narrative of the nations, and that's why you see the lot of tussle between the big players. They want to control how communication goes, right? And all that lies inside here in bandwidth, communication technology. Right, but if you remember, there was not lot of buzz on the 5G auction. You know the reason for that? So as of now, 5G is crawling. There have been a huge investment, lot of deployments everywhere, and in fact, if you see US and some of the advanced countries, the utilization of 5G spectrum is, or 5G technology is limited. So you have the way it works is you have the 4G deployment from tradition that is going on from last 10 years, and simultaneously you have a 5G network, and you have a fall over option. So if this doesn't work, you go back to the 4G, right? And then you try to see what is the utilization of this new technology that is being deployed. And the results that are coming out from US and other countries is very poor. Okay, so US is reporting a utilization of 12%. So that means 88% of the time while the phone is 5G, you're moving around with a 5G phone. 88% of the time you are still connected to a 4G network. It's only 12% of the time that you are getting connected to a 5G network. And we'll see. And because of this, the auction pricing for 5G was very cool. It didn't go very well or to the expectations of what our government thought. And it is an international trend because 5G is a very different technology from what we have been growing for last 4Gs. Because they're reworking based on some assumptions, and that's not working. So we'll go through that for that. And the reason I'm saying is this opens up a lot of challenges for signal processing. Okay, so there is a need of lot of bandwidth and technology for sustaining this high throughput. So one of the technologies that, in fact, the differentiating technology for 5G is massive MIMO. And the way this works is what I will be explaining in the next few slides. So you see that you have a base station, but this base station is different from 4G base station in the way that it has, you see how many antennas? Can you count? 1, 2, 3, 4, 5. Yeah. If you can count it, we are now speaking of hundreds of antennas, a large number of antennas at the base station. Okay. And because of that, you have multiple input. And when you want to transmit something, you have massive number of transmit antennas at the base station. You have lots of users, so adding them together, you have massive number of input and massive number of output antennas. Even though each user has assuming they have a single antenna, still users are always large. They are in hundreds for a typical base station. Okay, so now you are speaking of a approach where you have hundreds of antennas at the base station connecting with hundreds of antennas for the users. Okay, and that's why the name massive MIMO. And this is the game changer. And the reason is this. Okay, for challenges, we come to it later. What you see is when you have a channel matrix H that corresponds to what you transmit and receive, right? And we take Hermitian of that, multiply the channel matrix with Hermitian, that is its transpose conjugate, right? The resultant matrix is scaled to identity matrix, is a scaled identity matrix. Okay, and this concept is called as channel hardening massive MIMO. What does it do? If you have, say, you are 5 and 12 transmit antenna, 16 users. That's the first figure. Okay, you take the transpose, multiply that. The resultant, what you get, you see this, there are 16 users, please. Okay, so the diagonal elements are very, very large. And the non-diagonal elements, they are not zero, but they are very, very small. See that this is for 512 antennas at the transmitter. Okay, so what does this mean? Signal processing wise, you are just doing a simple transpose operation and multiplying with the matrix. Okay, so signal processing is simple. Result, what you are getting is there is no interference from the other channels, other users. Okay, the low coefficients uh, other than the off diagonal elements implies that each user is not interfering with the other users. The 16 users, they are only getting their signal amplified, and the signal from the other users is very low. That's the underlying understanding from this figure. And what you see is, if the number of antennas reduce, what you have is the interference slightly increases. You see the background picture here in the figure 5, 128. The number of antennas at the base station is 128, and same number of users 60. You see that while the component of the users from themselves is same, there is some interference from the users. This effect of reduction of interference from other users as the number of antennas increase is what is called as channel hardening, and this is the underlying principle of 5G massive MIMO. Okay, 5 massive MIMO works on this, and that's I say that this is the defining technology for 5G, and the reason is this. Okay, so while 88% of the time we are still using 5G, 4G, and we are now speaking of 6G. And the reason is of the way we have evolved over these decades. First, 1G introduced voice, but finally voice was workable. The phone, our mobile phone, was good for voice when 2G came into picture. Similarly, 3G introduced data, but it was pathetic. 4G made it really work. Right? We could do a lot of things. 5G, you're saying URLC, I'll explain it later on, but as of now, you assume that 5G is introduced, but we expect that this is going to be perfected in next generation. Okay, so already a lot of work has started in trying to solve the problems that are being introduced because of 5G. So going into the explanation of how things are working, you see that 5G new radio frequency bands have been divided into two slots: frequency range 1 or FR1, frequency range 2 FR2. And frequency range 1 is sub 6 gigahertz. Its frequency is below 6 gigahertz. So typically it's around 3.5 gigahertz, and some countries like UK, etc., also allocated some bands below 1 gigahertz. Okay, the problem here is the maximum channel bandwidth available in this sub gigahertz band is 100 megahertz. So the amount of data data rates you can support here is very limited. Okay, so frequency range 1, the data rates that is possible is probably a factor, maybe 3-4 times of what you get for 4G if you are working in frequency range 1, because the bandwidth here is limited. That changes when you go to the millimeter wave frequencies, that is 24 to 54 gigahertz, and 5G has put a lot of effort in defining this part of the frequency range, FR2. Okay, here the minimum bandwidth is 50 megahertz and the maximum is 400, allowing for aggregation, so you can go up further. The thumb rule, again, as I have showed you at the start, higher the frequency, the higher data rates you can support. But there is a catch. This frequency range on which the high data rates of 5G depend, okay, it has a huge problem because the frequencies are very high, and the very high frequencies get huge attenuation. Okay, so the channel characteristics become very unreliable. If we have lot of humidity, the signal gets absorbed by water. So these millimeter waves, they get absorbed by water molecules. So you see when if it is raining or if it is very humid, you see that there's a huge fading that comes into picture in FR. Okay, and it is sensitive to obstruction, reflection, etc. So if there is no line of sight here for millimeter waves, it typically does not work. Okay, so this was well understood way back. Remember the channel hardening principle. This was published in 2010. So Marzetta here, Thomas Marzetta, originally from Bell Labs, and then he shifted to Nokia in Norway, in Finland. So 2010, he presented this channel hardening concept. Okay, so it took 10 years for this technology to finally come to market as 5G in 2019, end of 2019. Right. So here, this limitation of this high bandwidth was understood, well understood, and so what they decided and what they planned was we'll have very small cells. Even though the cell size is coming down because of density, number of people they want to cover, and the data rates. So, but this 5G new radio for frequency range 2 was limited in range. You see here, femtocell tens of meters, urban areas micro cells, a few hundreds of meters, but hundreds of meters is not working. Even these tens of meters is actually now working only for few meters. Okay, so we are just able to at the max go to 20 meters in uh, typical deployment scenario. Yes, any comments? Any doubts?
No, sir. No, sir. Continue.
Yeah. Okay. So, but these were the projections on based on which the standard was made. Okay. So he said that okay, this is going to get attenuated. So let us take care of that attenuation, and the ranges were planned accordingly. Powers were fixed accordingly, and the number of users they would serve. A femtocell would be serving say 4 to 8. If it's a business area, 16 to 32, and if you go for a metro cell, a few hundreds of meters, the plan was 250 meters. Now 250 users. Okay, this is the third column of the table. I am seeing if you are able to see my mouse there. But in actual deployments, neither the femtocell nor the metro cell is able to support more than 12 users. Okay, and this is again because the channel hardening effect that I spoke of before here is not working so well as you see here. It is working worse than what you see here. So there is a huge interference coming from other users, and if you don't take care of this interference by proper coding, etc., or signal processing, this interference will saturate the throughput, your BER, etc., and so your system performance will become very bad. Okay, so those are the reasons why those are the problems that is now being faced by 5G. Okay, so I have discussed the problem, and I have discussed the problem in detail for 5G, what is going on. Okay, this channel hardening concept that is the underlying basis for massive MIMO, and also from the essential differentiating factor of 5G from 4G is not working so well. Okay, and there are other advantages of massive MIMO. So if you have large number of antennas, right, there are other different problems that come into picture. So for each antenna, you have to have an RF chain. That is very tricky because RF chains are very costly, and that contributes to one of the major components of cost for your mobile transmitters or your Wi-Fi sector. Okay, but you have large number of antennas, so there is a flexibility that they allow you to do beamforming for each one of the users, provided hardening works, but hardening is not working. Still, from 3G to 4G, there was a lot of improvement in quality, essentially because sophisticated coding techniques were involved, and space-time coding was involved. So MIMO was taken into the standards in pre-4G and 4G. So the major advantage in 4G came because of MIMO, not just simple MIMO coding or space-time coding. Because of this channel hardening concept, people felt that those space-time concepts are no longer required. Okay, so that space-time coding was removed from 5G for the FR2, the massive MIMO frequency band. Okay, so that removed a lot of signal processing from both the transmitter and receiver base station. But there's another problem there. If you do a lot of signal processing, space-time coding for say 512 or even 128 transmitter antennas, it takes a lot of time. It's not practical. Okay, so there's another conflict coming into picture. Uh, your channel hardening is not working, and you thought it would work, and because of that, advanced signal processing was removed. Now, if you want to bring it back, the number of antennas is huge, and this already deployed. It's already deployed. Okay, there's a huge investment in country-wise in many countries of the world where there's a massive investment on 5G, but it is not working. Okay, so now the problem is to address this. We want now to make this work as close to this figure as possible, while still having to make the signal complexity low, because already the number of antennas is huge and you have to do it for each antenna separately. There is a possibility of reducing the processing by replication, right? But replication does not give you good results. Okay, so there are other lot of challenges in massive MIMO, and which have not been addressed properly, and that is why you see most of the time, if especially if you speak to insiders working in 5G deployments, 5G is really not what it is expected. So another 1 or 2 years down, I'm expecting a 5G plus come up, because things have to change, right? And for us from signal processing, this means there is a lot of work to do. Okay, so the answer is signal processing, and of course more signal processing. So when I introduce RIS, and I will say that RIS is going to be the defining approach for 6G. 5G was massive MIMO. There are problems, we'll solve it. Okay, so people are working on it for everywhere, because huge billions of dollars have been put into, so people want it to work. So a lot of investment is being done to make it. So one solution, I will put it here as an example. Okay, there's a lot of work to show, but I'm just give you one example. So what you have is a massive MIMO system with huge number of transmit antennas. Okay, that data is being received by different users, and this process of transmitting and receiving is modeled by your MIMO channel. Y is what you receive at the different users, say y1, y2, yn. You collect that, so you get a vector y. Okay, the number of transmit antennas at the base stations, u is the number of users. Okay, so base station is transmitting on B antennas, and that is being received by U users. Okay. In the uplink transmission, it is the users that will transmit to the base station. Downlink, it is the base station that will transmit to the users. Okay, so accordingly, the dimension of the head channel will change. We'll get a transpose. So this is the massive MIMO model as seen at the base station. So users are transmitting all the signals from the users pass through the channel, which is represented by the matrix H, okay, complex matrix, which is of dimensions B cross U. Is this model clear?
Sir, clear,
Yes.
sir.
Yeah. Now, if you do normal decoding the way we do in digital communications or we do in massive MIMO, we try to find the minimum distance from the received vector y by uh, comparing with all possible x vectors. So suppose each of the user is using BPSK, so that would be 2, and in our model we have u number of users, that will be 2 power u different possible x vector. Okay, so that becomes 2 power 16 is small, but when you go for higher modulations, it becomes very difficult to work on this. So this optimal solution or the maximal likelihood approach to get estimate x when you receive y is not possible. It is very complex. Okay. So if you are using MRE modulation or say 64 QAM modulation, this would be 64 power 16. No computer will work there. Okay, you need a supercomputer to solve the optimal solution. So this optimal detector is no longer workable for the massive MIMO concept. So you need a simpler one. So what is typically used is what is called the match filter. See again, go back here. H is what is the channel. Okay, it's the attenuation, rotation, etc. that your signal that is transmitted from different users is received at the base station. Okay, so the match filter that is typically deployed everywhere, and that is the solution that has been deployed. You just multiply the receive vector y by the Hermitian of the channel H, and on that channel you make the assumption. Going back here, this would work if your channel handling concept works. If it were like this, there would be no interference and you can decode each user independently, separately. But if it is like the figure second, figure 5, where you have lot of coefficients from other users coming, when you add them up, okay, for 16 users, add them up, it will see it is around 0.2. Okay, for 16 users, so the interference signal will now be greater than the actual signal that you are trying to decipher. Okay, so the solution that people thought would work for match filter because of the channel handling concept is not working. But because you cannot put in lot of complexity, this particular solution is what is typically used in practical implementations. Okay, because you need to do all these number of multiplications within a fraction of a second. In fact, it is a fraction of microsecond because your data rates are in gigahertz. So the amount of time that you have to do this much of processing, see, you see it's a matrix vector multiplication. Your H is of size 512, Y is of size 16. Okay. So how many computations it would be? How many multiplications? $16 per row 16 multiplication. How many rows? 512, right? 512 into 16 multiplications you have to do in fraction of a microsecond. Okay, so this simple multiplication itself is very, very costly because of the number of antennas. Okay, and it is not working. The other solutions that were possibly thought in papers but not in actual deployments is your zero forcing detector, where you use the inverse. Am I audible? Yes. Am I audible?
Yes, sir. Yes, sir.
Thank you.
Yes, sir. Yes, sir.
When you are not able to follow or you have some doubts, please do ask so that it's interactive. It becomes more interesting, and I can give more of the data that I have. Otherwise, it would be just a single one way. So I would encourage you to ask questions if you have.
Yes, sir. Dear participant, please, you can share in the chat box.
Yeah. So continuing. So the other approach is to invert the channel. We take the inverse, but your H is a tall matrix. It's not a square matrix. It's a rectangular matrix, a special type of rectangular matrix, right? So you cannot take an inverse of it directly. So when you multiply by H, and then you take an inverse of H Hermitian H. Okay, so that is with this approach, you are guaranteed that you will get an I. That is, you are cancelling interference from the other users. Okay, but what is the size of H Hermitian H? See here, your H is B cross U. So H Hermitian H would be, come on, it's just matrix multiplication. H Hermitian into H, where your H is B cross U. So what is the dimension of this matrix for which we are taking inverse? It will be a U cross U matrix. Okay. So while it is not large as number of base station antennas, it is still sizable. Even if you take 16, you have to invert a 16 cross 16 matrix. And inversion takes n cube. So it is 16 cube computation. So that's why even this simple zero forcing solution is never practical at the present. Okay, so you have to in a similar norm that traditionally decoders, the detectors that were used at the receiver, you have the minimum mean squared error or linear minimum mean squared error detector, where you take care of noise also being added. So this particular detector minimizes or maximizes the signal to interference noise ratio. Okay, so these are the traditional detectors, and since we want simple detectors, one of the three were the candidates, and in fact, practical solution only the match filter, the first one has been the only candidate. So how do we go forward from here? Okay, so you see computation of H Hermitian, that itself multiplication of matrices takes BU square. Then you take inversion, that is order of U cube. So the complexity of inversion is typically not possible. So what people have done is approximate detects. So you have iterative methods based on, we have been working in any area of signal processing. You see that these methods are well known. Okay, in fact, even if you remember from your basic maths M3 courses, you have the Newman series, Newton-Raphson, iterative method, etc. They are basically trying to approximate how you are getting the inverse rather than finding the exact inverse. So the successive over relaxation, Gauss-Seidel method, gradient descent method, these are all conjugate gradient method, these are all approximate iterative methods to reach the inverse. But you see that the complexity is, while being reduced from U cube to U, okay, depending on the detector, okay, you have 4BU square coming in. Okay, so the complexity is still sizable. So can we do something more here? So what we have proposed in one of our papers is what's called the Hamilton based eigenvalue detector. So the principle is simple. All of must from your maths courses, where you have done matrix, you should remember that Kelly Hamilton is an approach to get the inverse. You write the characteristic equation, take out one of the A from the one side, and then you are able to calculate your inverse from the characteristic equation, right? So that's the principle we are using here. G is your H Hermitian matrix. approximate it to IU. So take a determinant of that, and you get your characteristic equation as lambda 1 minus 1 over U, right? Expand it. So this is the expansion you get of lambda minus 1 over U in terms of the G matrix, right? And take one of the G to the G inverse multiply other side, so you reduce the coefficient by 1, right? This is a simple Kelly-Hamilton based approach for finding inverse, which most of us study in M2, M3, right? But this simple solution actually reduces complexity by adding another simple approximation. So you see here also, you have a lot of matrix multiplications. But what we suggested was, let's not do matrix multiplications. Let's first do each multiplication step by step. For example, see equation 3. Our approach of finding zero forcing approach is G inverse replaced by this series, then compute each one of them in one time. For example, first compute H Hermitian Y. So it's a matrix vector multiplication. So the complexity is reduced by order of 1. No, 6G is as of now, those general questions I will take at the end. But the maths that I am trying to present now, we'll discuss that as of now. I'll take your general questions on 5G, 6G towards the end. Okay? I'll finish another 8 minutes, but I want to give you some 1 or 2 concepts. So rather than doing matrix multiplication, we suggest that we first do. You're not audible?
Now audible, sir. Now audible.
So what I said was, the questions that are coming in the chat, we take it towards the end. They are general questions. I will take questions related to the maths that I'm presenting now. These general question on 5G, 6G, I will take later on. Okay? Yeah. So what we first suggestion that we gave was use Kelly-Hamilton theorem, replace the eigenvalues by 1. Okay, so that gives a very simple series, and then do matrix vector multiplication at a time. Yes. Still not audible? Hello.
Audible, sir.
Breaking, sir. Voice is somewhat breaking. It's good, sir. Fine now, sir.
Right. So what we are suggesting, if you first multiply hy, so you get another next vector, then multiply with that vector with g. Okay, that will become g square into h Hermitian y. So you replace matrix multiplication by matrix vector multiplication. So that approach has reduced the computational complexity by a huge value. Okay, it's an order of magnitude reduction. But there is some problem here because we have used the approximation. See here, we are still approximating G by I, which is not correct. So while this is an approximate characteristic equation, it is not correct. And if we try to see how the working of this, for such a G matrix, the minimum and maximum eigenvalues are distributed according to this formula. Okay, and what that means is, if B by U is greater than 1, then lambda max is near to 1. Okay, and then the proposed approach converges to the G inverse property. Otherwise, it diverges. So what happens is, we have conversion issues with this sort of approximation. So we said that rather than doing this, we'll take the largest eigenvalue, 1 plus UB, and we appropriately define the characteristic equation as lambda minus lambda max. Okay, so what you see by this approach, this slight change in convergence is very good. You can see here, complexity wise, we have reduced by from u square to bu square to bu and u cube to u. Okay, so that's a huge reduction in complexity that is possible, but still this approach is not very feasible unless we go to parallel computation, but I will not give you details of that. The important point that I wanted to highlight here is there is a lot of signal processing that is coming into picture. One slide to see how the problem is coming, where the problem is coming, and how to address it. That's one part of it, and the other solutions for that. So you can see that this the top curve here is for just the match filter, and the moment we introduce our approaches, you see this is a significant improvement in BR. In fact, if you see the black curve here, there is a saturation in BR. So your performance is getting bad, and it's not improving even if you increase the SNR significantly. Okay, so we did other analysis. The other solution is more signal processing. So till now, what we are trying to do is do much more intelligent processing at the receive. The other approach is what is called as reconfigurable intelligent surfaces, and that is what is the technology we think is going to define 6G. Okay, the approach is highlighted in the next few slides. You have the transmitter and you have a receiver. It's the environment that is giving you the channel H, right? Till 5G, the approach is to optimize your transmitter and receiver so that you reduce the bit error rate and maximize your throughput. Okay, this is the net or the eagle's eye view of what we have been doing till 5G. Okay, so the adaptation signal processing is at the transmitter and receiver. The channel is untouched. You don't touch it. You cannot do it. At least that was the perspective till now. Okay, that's changes now. You see in this slide, what we are doing is we now want to change the channel itself. We want to make the channel controllable. How will you do that? Is anybody? The answer lies in the definition of what we are saying: reconfigurable intelligent surfaces. Okay, so what you have a transmitter, you have a receiver here. In addition to the signal you are getting from the transmitter to the receiver, you want the signal to be reflected from other places where you have put some sort of specific reflecting surfaces, which is doing in such a fashion that the signal here gets enhanced. Remember, there will be, without the RIS, you will have reflections, but they are uncontrolled. You cannot control them. Okay, so they may combine properly, so you'll get a good signal, and they may not combine properly, so you'll get a bad signal. So in this case, what you are trying to do is you are going to manipulate the reflection coefficient, and that was not possible before. It is possible now because you have advancement in meta surfaces. So we are using material science to actually enhance the way the transmitter and receiver are interacting with each other. Okay, so your RIS, in this picture you see we have put RIS in 3 places. Okay, and if you see, for this user, there's no direct part at all. There was no communication. But these 2 reflections are making it possible for this user to receive the signal. Okay, and see, the importantly, it is line of sight. For line of sight from here to here, line of sight from here to here, line of sight from here to here. Okay, so that's the concept of reconfigurable intelligent surfaces. The other names also that people use in literature, but RIS is the generally used wording because of political reasons. Okay, so the important point as compared to 5G and 6G is we are trying to now change the channel. We are trying to put optimization into the channel. So we have to control how the reflecting surface works, and for that we need to gather data and do some processing. So this involves both control and AI. So we are actually putting up something more, significantly more, to make things work properly. Okay, so that's a paradigm shift. Okay, proposed just in 2020. You see the paper just end of 2019. So till 5G, we have tried work with the channel by using massive MIMO, some coding, something at the transmitter. But now with RIS, which we think is going to be the defining characters of 6G, we are now trying to change the channel itself. Of course, because of the frequency we are working, that is millimeter waves. So that means huge number of antennas. So adding RIS will add an extra computational complexity. So underlying principle for all of this, it is not the solution. In practice, lot of what we have tried to go to this. Yes. I am not able to get you.
Sir, clear, sir. You can proceed, sir.
Yes. Okay, so there are many possibilities that you can do from reconfigurable intelligent systems. So one example is polarization control. You can control the scattering, or you can focus the beam the way you want it. Okay, so massive MIMO with RIS, we think is going to be the for the 6G, and that's where we are investing most of our work. Okay, and there are other approaches, and all of this would require still, because the amount of computation is required. I'll skip the part. Complexity wise, we are still going down, reducing the. Okay, but the important point here is we now need parallel processing, and parallel processing, people have started working in this particular area because they do started saying is, see, you have a series and for parallel processing I is working into. So I have enough for taking that. So what we have tried to do is do each, or rather factor computations to different computers and allow parallel processing, because time is of principal concern in all these parts. You have to do it in real time, and that real time also is per second. Okay, so there's a lot of needs to be done to make these things feasible, but underlying assumption what I say is, yes, we have started something to be working. So we are working more. So solution is signal processing and more signal processing. I have given you a few examples of that, right? So with that, I'll conclude my presentation here and we'll open up to question and answers. These are some of the papers that we have published while working for this particular area. And there are lots of in parallel, especially for RIS, and we'll discuss in presentations when those get published. Yes, to the question of range of CG base station, actually, it is too early to say that. But if you remember the slide number 5, with different powers, you will cover different able to achieve that, and probably our target for 6G will be achieving those ranges for millimeter waves. See, yes, when a signal gets reflected from a surface, right? It polarization changes, right? So reflection coefficient that you are making intend the reflection coefficient. So that reflection coefficient will change the polarization. Okay. Yeah. Too early. We are many countries are still going to start to picture, but yes, RIS based what do you say, test beds or lab trials are being reported. Yeah, as usual, two countries who lead in these two areas, US and China. There's work in other countries also. I have not seen any practical RIS test beds in India. Would expect people to work much more on this, but yes, as of now, no. Yes, any other questions?
Yes, sir. Sir, am I audible, sir?
Yeah. Yeah.
Yes, sir. I am very much curious in knowing that, sir, how long we will go from 5G, 6G, 7G. Is there any limiting factor in that, sir?
See, as of now, it is growing exponentially. Every time people think that it will saturate, but it's not saturating it. And as we connect every device and every and we are putting sensors in every place, I think at least demand will increase. And demand will get a new level. New generation next. RIS would have not been possible 10 years back because that technology of being able to change the reflection coefficient was not practical then. It is now practical.
Yes,
right? So with technology advancements, new things will come up. Question of that match filter comes problem with the match filter, right? So you can adapt, but you need to estimate also for adaptation, right? So that in itself involves additional complexity. But what I see rather than going that being adaptive is because some part of the you don't know and you will not know. Okay, not know. This hardening effect that I discussed for Massimo does not work because of 2-3 reasons. First is saturation. Okay, second is poor channel estimation, and when you put large number of antennas, you have other that like coupling, so your signal gets correlated. So all those tend to saturate your signal. Okay, that basically gives you the saturation effect in your signal. So those things you cannot change by using an adaptive match filter. You need to put in technology. Like from 3G to 4G, the major difference was space-time codes being put into picture. So some of those sort of things have to be brought back. That is my hunch.
Yes, sir. Yes, sir. A very warm thanks, sir. Thank you very much. We blessed. Sir. Voice is breaking, sir, I guess.
No issues.
Okay, sir. Okay. Now, HOD, sir, please, sir, conclude, sir.
Sir, thank you very much, sir, Jafar, sir. So thank you for a wonderful session today. Once again, I thank you from the Department of Electronics and Communication Engineering, NSRIT Vishakhapatnam. So we thank you very much, sir.
Thanks, sir, for the invite. I hope at least I have made somebody interested in these areas.
Nice, sir.
Yeah, yes, sir. Yes, sir. No, sir.
Sir,
बहुत शुक्रिया, sir.
बहुत शुक्रिया, sir. मेहरबानी, sir.
So I request all the participants to switch on the video for a while. Request all the participants to switch on the video for a while for a screenshot. Thank you, sir. Thank you very much. Now, Gautami, you can proceed.
Now I request Dr. Virendra Singh sir to talk about research proposal writing.
Yes, madam. Yes. Professor Jafar Ali Khan Mohammed, sir, thanks for coming, sir. Now, okay.
Thank you. So, and I from my side.
Yes, thank you, sir. बहुत शुक्रिया, sir. Thank you very much, sir.
Bye.
मेरे को स्क्रीन शेयर करने दो, PPT. Dear all participant, I will take only 15 to 20 minutes. After that, we will close this session and we'll go for the final validity function. So stay tuned for another half an hour and then FDP will be over. And one mandatory information is that everybody has to fill the feedback form. We will be sharing just after 15 or 20 minutes. So stay tuned. I request all the participants. The slides are audible?
Yes, sir, visible.
Okay, sir. Okay, thank you. So in this session, we are going to discuss how a project proposal we can write and how many things we have to consider in writing project proposal. It is being it's a common thing that most of the people, I find so many people who are very comfortable in doing their research, but whenever it is asked then how to write a research proposal, what are the components of research proposal, a little bit of gap or ignorance is there. So this session we have introduced for all the participants to just have a look at an example. How can we write a project proposal? It's just an example like design, development and fabrication of MEMS based high G acceleration threshold switch. Suppose you have to present a project proposal on this type of topic, then how you will be doing that, including cost analysis as well as the duration. So first of all, this would be the probably outline for this type of project proposal. Personal detail of PI and co-PI, aim and significance of the project brief, and IPR matching means what is the international standard of that particular topic, what is the national standard of that particular topic. Then most important is are you comfortable in reading all the papers, all the literature, all the patents related to this, like what kind of research gap you have observed in the literature. Say research is not a thing that you have to transform a measure or significant effect. It's just keep adding on one by one, brick by brick, some delta addition to the previous one, and then next person will put another delta, and things are going on from past so many hundreds of years or thousands of years. Next, novelty or value addition, what you are proposing, what is the additional thing you are going to add, And then R&D partner, most probably you should choose as a few partner as per the scope of the project, then plan of work for the project, budget, and deliverable at the end. Next, principal investigator, of course, education, background, experience, and then co-PI. Selecting a co-PI is again a crucial thing. You are not supposed to pick co-PI randomly to just fill up it. Why they have permitted more than one co-PI? Because suppose you are going with this project and you have to fabricate this device. Then for fabrication, I have taken one co-PI, and then for design and testing purposes, which are the end user like DRDO. This project is basically asked for DRDO. That's why we have chosen one co-PI from there. So choose your co-PI as per the scope of the project, as well as the quantum of work, means how they are going to contribute, not just for big names or like that. Then introduction to this this technical things you don't consider because it's very deep inside. So you just have to introduce in what technology you are focusing, what kind of what is the end user for this project. So this switch will be used in fuse, and fuse will be used in armament, and armament will be used by DRDO or armed forces. So we have to include all these. Then what is your technology? What is the basic shaping, arming, and firing right here? So fuse must be able to do this. Then next slide, it is we included which material you are going to choose. Like silicon is the ideal MEMS material. We have seen in yesterday as well as today from Ayan Karmakar sir. Sir, silicon is basically the due to its huge potential, and it can be used like 1/3 of densities to steel, hardness one half of steel, and young model with good young modulus and yield strength around 2 times than steel. So batch manufacturability, already we are having VLSI processes, so you're using the same processes. You can go for MEMS also. So this kind of scenario or this kind of logical explanation you have to put why we have chosen silicon or any material as per your project. So these are basic insight. Then aim, design, development of fabricated MEMS based switch, significance of the project, how it is significant, why you are designing it, to whom you are going to deliver this, or if this is related to army or defense organization. But if you are designing for any basic, or you are solving any basic problem like sustainability, like water, or any kind of like communication, any field you are going to target, you have to tell why this project is very much critical to use. And another thing, if you are dedicatedly designing one sensor or one thing or one process or any research you are going to do, so you have to tell also the alternate applications. It will be better and with advantages as well as the most recent advancement in that switch. Next, IPR matching. It usually starts with how many publication, how many good publication, good journals, or how many scientific platforms where this topic is being discussed. Like we were discussing 60 in the previous lecture by Professor Jafar Muhammad Ali Khan. So the prominent thing is that you have to be in touch with the international as well as the national standard. Right now, IPR matching, you can include all the possible patents, latest patent related to that. Then research publication, national, international, both touch or both flavor you can give. And before choosing publication, one thing I would like to share that first this is kind of approach when you gather, you found yourself with maybe 100 papers, and then you have to segregate which topic or which technology you are going to target. Suppose first of all I am targeting MEMS, then into MEMS I am going to target inertial MEMS, then inertial MEMS I'm going to target high G acceleration threshold switch, then what kind of switch, whether it is latched or non-latched. This is just an example. So in the same way, whatever domain you choose, you have to go like in this way, and you have to collect all the relevant paper, so that after reading your research proposal, anybody reviewer would be able to get some flavor of that. Just by reading that, that individual should get the flavor of everything about that topic. Suppose you are claiming that I will do this, or I will target, I will design, and you don't know the current status of that technology, then it's irony. So you can't go like you don't know what other people are doing, and then you can't claim that I will do it will be unique. So you have to do extensive research or extensive review for that. Then along with the, so as per this topic is concerned, so I have taken a crucial paper which is being reported in the literature, and then try to find some gaps. What are the gaps? So in this topic particularly, non-linear dynamic response of MEMS based high-G switch under mechanical shock is not perspicuous. Why this word is here? Because sometime if many literature have been reported on any particular area, so sometimes things are not clear. Like in this, they have taken some dynamic factor randomly 1.8 for, and then justification is not there in the literature. Then I, in my PhD thesis, I have justified this, that why I have taken this 1.8. Then out of those research gap, you have to put your research objective, what you are going to do in this topic, and novelty or value addition. So whatever you are contributing, right? So in like in this project, we will ensure that no power will be required. Like accelerometer require power for its operation, but this switch will not require any power. In the same way, you have to tell the novelty and value addition for your project. Then R&D partner and beneficiaries means the R&D partners for this project, Semiconductor Laboratory Mohali can act as a fabrication partner for it, and Terminal Ballistic Research Laboratory DRDO is the user, or is the not end user, but it is the receptor of this type of technology. Then plan of the project. You should have a clear picture in your mind what you are going to project, starting and in step by step. It's not like that you will start randomly, just simulation design and you'll start randomly. No, literature, extensive literature survey, empirical calculation for anything theoretical. Any engineering problem can be solved in three ways only: theoretical, simulation, experiment. You have to design your project as per this flow. Then after getting satisfied with the Excel or MATLAB or whatever you are doing, then you have to go for design and simulation, and then fabrication, packaging and testing of the switch. So budgetary, you can see that you have to plan your budget in such a way that each budget in the next slide, justification will be required for each budget. Like how many manpower or how many staff member you are required for this. Then what are the consumables, contingency, travel, overhead charges. You can split your budget as per this. Next is the justification for this budget. Why you are asking this budget? One of the most important thing, whenever after technical screening in any organization like DST or like that, after technical screening, you will see that the second thing they only see at the budget, how budget is being distributed. So manpower, you have to justify; consumable, how many is required; contingency, travel grant, overhead charges, what you are using for the institution, and like this. Then milestone and deliverable, you have to show in the cumulative way. Like in first 4 months, some theoretical aspect will be studied. In next cumulative 9-month design and simulation. By end of 18 months, fabrication, packaging, testing of that switch, and then report, paper writing, and like that. And then you have to present what you are going to deliver after this project. Right. So these are, and at the end you have to put the reference. So thank you very much. This is just a quick reason because we are short of time. We have just put 15 minutes for this activity. And if you do have any question regarding this, then you can share or you can ask me. Any question?
Virender sir, good afternoon, sir.
Yes, madam. Good afternoon.
Hello, am I audible, sir?
Yes, very much audible, ma'am.
Sir, you have explained about research proposal writing.
Yes,
in that topic, research gaps you have mentioned, sir. That
yes,
is explained about your project.
Yes, ma'am.
But I didn't get in detail, sir. Could you please explain with a simple example?
Sure, ma'am. A research gap is something which you are, whenever you are going to read literature, suppose you have read a few papers directly related to that topic, and you are you found something is missing. Like in my project, what was missing? there is a difference between static and dynamic response. There is a factor, like if and that factor is taken in literature 1.8. Then why it is 1.8? Why people are not taking 1.5 or 1.4 or 1.1? Then I found this reason by extensive analytical solution. I have used Duhamel integral to derive the shock response spectrum, and from that integral or that nonlinear analysis, I found this gap. So, as per your topic, suppose you are in antenna, right? Suppose you are using an antenna, then you have to find what is lagging. Means like if you see flexible antenna. For nowadays, flexible electronics is trending. Everybody want to design some flexible PCB or like that. So next gap you will find, okay, whatever is being there, I will make that flexible, or I will reduce the size, or I will increase the performance. Any parameter which you think that this can be improved, and research gap, and make your objective and go for that.
Then how can we overcome that? Overcome means how can we update that answer in next proposal, or
no.
How can we overcome that gap?
Yes, ma'am. See, whenever you are presenting a research proposal, nobody is asking for your for your solution. You have to just identify the problem, and you have to put in your objective, and then you will take this mission in your hand, and you will find out the solution. They will not ask for they will not ask for the solution. Asking question can solve problem 50%. Asking right question.
Okay, sir.
Because after that we will get the way where we can go. I hope this will help.
Thank you, sir.
Okay.
Definitely, sir. Thank you, sir.
Any other question? And then straight, if no, then we will move towards.
Thank you. Virender, you are on mute.
Okay, sir. Okay,
thank you.
It's again. So thanks all the participants. We are very happy to see your patience level. You are continuously attending this FDP, and we have arranged typical or premium resources from ISRO or IIT, NITs, or from industry. We try to touch, not so common topic like plasmonics or nanomedicine in nanotechnology or 6G. People are talking about 5G, but we thought that we should go ahead for 6G. So that's it from my side. Any question, you are welcome. And please don't forget to fill the registration form, feedback form, and we will start the validatory function right now. Just any question, then otherwise we will move to that direction. Sir, we can proceed, I think.
Yeah. Thank you, Dr. Virender, for your exposure on given a good, nice talk on writing a paper research proposals. Any questions from anybody?
Sir, ask all the participants to switch on their cameras for the validity.
Yeah, I request the members, all the resource persons also. I once again welcome all the resource persons for the validatory function. So please kindly switch on the camera once.
I request all the participants to fill the day 3 session 2 feedback form and attendance form immediately.
Sir, should we start the validatory function right now? Dr. Bisu Prasad, sir.
Yes,
sir.
Yes. We can. So please share the Google form. Feedback form. Even the check whether the resource persons have joined.
Sir, we have requested you just start. They are saying they start. They will join.
Gautam.
Start.
I hand over the session to Dr. B. Shivprasad sir, HOD, Department of ECE.
Okay. So very good evening and a warm welcome to all of you once again to this valedictory session of a 3-day FDP on emerging trends in electronics and computer engineering at Department of Electronics and Communication Engineering, NS Raju Institute of Technology, Visakhapatnam, Andhra Pradesh. So over the last 3 days, we have had a deep insights into the diverse topics related to electronics and computer engineering. So starting from the first day, started with welcoming our chief guest, Dr. P.K. Koshla, Pro Vice Chancellor, Chitkara University, Punjab. So Sir has delivered an outstanding talk on healthcare after post-COVID situation, how the things have gone and what are the precautions we should take. So Dr. P.K. Koshla sir has given an outstanding lecture on healthcare. And after that, our first speaker, Dr. Manish Kalra, assistant professor from NIT Jalandhar, gave a basic introductory lecture on machine learning and their applications. And later, our second speaker, Dr. Vinay Loshev, scientist, data scientist from Data of Gurgaon, gave an outstanding lecture on applications of data science in the medical field with a great clarity to define the scope of various fields like data science, machine learning, and artificial intelligence. And Sarah has cleared the doubts of almost all the participants. Those are raised. And the second day was very productive in the FDP, consisting of 4 sessions, starting from Dr. Sachin Kumar Srivatsava, assistant professor from IIT Roorkee, with an outstanding emerging topic like plasmonics, fundamentals to applications by touching different domains involved from physics to machine learning. The second speaker, Dr. Anvesh Kumar Nella from VIT Bhopal, gave a beautiful and interactive lecture on directional ultra wideband and terahertz antenna technology. So almost many of our participants cleared their doubts about antenna designing. So related doubts they have cleared. And coming to the third speaker, Dr. Sripad Raja, a product manager from IntelliSense India. So he has Sar has delivered an eye-opener lecture on topic simulating MEMS devices, and also Sar has told the participants that how one can approach the MEMS fabrication facility worldwide. So with the cost efficient approach kind of thing they explained. So it's a beautiful session by Dr. Sripad Raja sir. And the final session was delivered by an outstanding scientist from CSIR, CSIO, Chandigarh, Dr. Abhay Sachdev. Sir has taken on emerging domain of nanotechnology, that it is nanomedicine and its applications. Sir has discussed about nanomedicine and its applications. And the first session on the day 3 was delivered by Mr. Ayan Karmakar, who is a senior scientist in semiconductor laboratory from Mohali on MEMS. So, which talk he gave delivering on promising technology for future generation wireless communication. So, and then the second session was delivered by Professor Jafar Ali Khan Muhammad from IIT Hyderabad on signal processing for 6G. So, which is a current emerging communication technology among the researchers. So, very useful those who are doing research in 6G in the area of communication. So, and last the session was handled by Dr. Virendra Singh, assistant professor from NSRIT Visakhapatnam. So he gave a brief talk on how to write a project proposal. And then overall, I could say this FDP is very productive and useful for all the participants to enhance their understanding into these topics. So my sincere thanks to all the resource persons, starting from Dr. P.K. Koshla, Pro Vice Chancellor, Chitkara University, Punjab, and Professor Jafar Ali Khan Muhammad from IIT Hyderabad, Dr. Sachin Kumar Srivatsav, Assistant Professor, IIT Roorkee, Dr. Abhay Sachdev, CSIO, Chandigarh, Mr. Ayan Karmakar, Senior Scientist, Semiconductor Laboratory, Mohali, Dr. Sripad Raja, Product Manager, Intelligence, India, Dr. Anvesh Kumar Nella from IIT Bhopal, Dr. Vinay Locham, Data Scientist, Data Org, Gurgaon, Dr. Manish Talwar, Assistant Professor, NIT Jalandhar, Dr. Virendra Singh, Assistant Professor, NSRIT Visakhapatnam. So, the participants who have, I once again thank all the participants, all the resource persons from bottom of my heart. As a convener, I could say the 3 days were very fruitful, and I think the participants would have taken something out of it. And hopefully, we are going to have one more FDP. So after discussion with the team, our team, we are going to announce one more FDP soon, very soon, on latest trends and technologies. So, and I request all the participants who have paid for the hard copy of the certificate will be sent through the post within a week. Don't worry about it. So we'll work on Monday about all these things as per our the things, and I hopefully you are going to reach hard copy certificates will be reached to you within a week. And for the rest of the participants who have attended this FDP will also get the certificates to their registered email ID, the soft copy. And at the outset, I would like to thank our Secretary Sir, Dr. N. Prasad Raju Garu, Treasurer N. Sri Kanakaraj Garu, for providing a lot of all the resources over here to organize this wonderful FDP. And our Director, Dr. J. Raja Murdas Garu, who has supported morally in all the ways for organizing this FDP successfully. And I thank the academic advisor, Dr. A. Shesharao Garu, and I thank co-convener, Dr. Virendra Singh, and I thank all the coordinators, Dr. K. Ravikumar and Mr. B. Ravichandra, and I thank virtual hosts of the FDP, Mr. Sheikh Sultan and Ms. Gautami Naidu, and I thank all the entire team of ECE department, NSRIT Visakhapatnam, for their continuous support during these 3 days for making this FDP a grand success. And I thank all the HODs of the other departments, faculty, fraternity, and all the participants from various institutions across India. Thank you one and all for your wonderful support for these 3 days. Have a good day. That's it for today. If anybody have any doubts, you please fill the Google form, feedback form.
Sir, I request participants to have their video on and give some feedback, video feedback,
yes, now
instead of
that is
live feedback.
Yes, I request any participants to talk about this FDP so that we can have a better FDP in future. Your suggestions are welcome. So maybe something maybe goes wrong, but hopefully we have done in positive manner without any delays or without anything, any problem. Hopefully you have learned something, and I request some of the participants to give your feedback, valuable feedback, whatever it may be. We consider it and we will consider your feedback. And I request the participants to speak for Sultan.
Yes, sir.
You please unmute those who raise the hand.
They can unmute, sir.
Yes, participants can unmute and you can speak.
Sir, 1 minute, sir. I will post the overall feedback from the 3-day FDP in the group, in the chat box. Please, I request all the participants to fill the overall feedback and post your comments so that we could make more. That will be posted in the group and it would be concluded after the meeting. Even it will be posted in the WhatsApp group. So I request all of you to make it fast. Now the participants can unmute themselves and give their valuable feedback.
Please introduce yourself and please let us know your valuable feedback.
Am I audible, sir?
Yes, sir, audible, sir.
Sir, myself, Sheikh Javed from University of Kashmir, Srinagar, JNK.
Nice, very nice, sir.
Very happy, sir, to see.
Very happy to see you.
Thank you, sir. Thank you, sir, for such a kind words. Actually, the FDP has been very informative. I have attended so many FDPs so far, but the topic which were covered during these 3 days and the resource persons were exceptional, and the managing of the FDP was exceptional also. So I thank from the core of my heart, and I'm expecting that in future you will enlighten us with such FDPs. Thank you from my side. Thank you from the Valley of Kashmir. Thank you, sir.
बहुत शुक्रिया sir. बहुत शुक्रिया.
Thank you, sir. Very nice. Thank you. It has been nice to see you people. You have been very kind.
हमें बहुत अच्छा लगा सर. हमारा मकसद यही था कि सारा इंडिया से सब जगह से लोग आए.
सारा इंडिया, कश्मीर से कन्याकुमारी तक, sir. You have connected the whole India.
Thank you, sir. Thank you.
Heads off to you.
ठीक है सर.
From very बहुत मुबारक हो सर. बहुत मुबारक.
शुक्रिया जी.
शुक्रिया सर.
Hello.
Yes.
Anybody?
We request other participants to please give your valuable video feedback.
It will improve our way of performing, and so that we can produce better learning platform next time, more than this.
I am Dr. V. Suresh.
Thank you, sir. Yes, sir.
Go on, sir. Suresh, sir, please go on, sir.
I am Dr. V. Suresh. I did my BTech ECE, MTech Computer Science, and PhD Computer Science. I am very much interested in antennas, and also that MEMS. So the project and all related to the computer and electronics, I make sure that I will give a proposal to that space. Thank you.
Definitely. Thank you, sir. Thank you very much, sir. Definitely. Any of the participants, I request the members to share your views.
Dear participant, please share your views. You have shown exceptionally temperament to attend this FDP continuous session.
Yes.
We are very happy, and you can share your views.
We are very much happy from our side because seeing the crowd, every time it is not less than 70 for the entire 3 days, any session. It touched around 100 also. But the people shown good interest in FDP. So we are fortunate to have the good resource persons also these 3 days. Anybody can share the views.
Good evening, sir.
Good
Yes,
evening,
madam.
Hello.
Good evening, madam. Madam, please switch on the video
And unmute, ma'am.
Unmute, ma'am.
Good evening, sir.
Good evening, madam.
Yes, madam.
Yes, sir. Sorry, sir. My video is not working properly.
Okay, no problem.
That's
No
why
issue, no issue,
I'm
madam.
unable to switch on.
No issue, ma'am. Please speak.
Hello. Disconnected.
Maybe some interruption is there, sir. Okay, she can make it later on.
Any other participants, please respond.
You can fill the Google form sometime later also. Please give us your feedback, please.
Good afternoon, sir. This is Devi Pradeep from Anit's College.
Good afternoon, madam.
Good afternoon, sir. Good afternoon, sir.
Sir.
Yeah, start my video. Okay.
Sorry,
yeah. Nice to see
yes,
you, sir.
Yeah. Suprasad sir is a good friend of me, arranging so many FDPs and conferences, even inviting all colleagues and earlier friends in the ECE domain. So happy to interact with you all people, sir. Virendra Singh, sir, your presentation is very nice.
Thank you, sir. Thank you.
Think in that direction. And the way which you are presenting and the way which all expert resource persons are presenting is very nice, sir. Actually, this workshop is not boring, sir. Only they are telling insights and emerging areas, sir. It's so nice to interact with all the people and learning. And first of all, as a faculty, we should be concentrating both on teaching and academic admin and as well as research, sir. So this workshop is giving insights in the area of MEMS, 6G in the signal processing, and all the things are covered, sir. Maybe in future, maybe from our side or your side, we will target towards the VLS areas, sir.
We would be
happy.
So
thank you.
That's what from my side, sir. So Professor is very well organizing and
thank you, Pradeep, sir.
All faculty members. Very nice to interact with you all people, sir. Thank you, sir. Thank you.
Yes, sir. Our boss is very much dedicated and time oriented. That's
Yes,
why FDP went through when 1 minute is not lapsed by sir.
Correct,
No,
sir. Correct,
we are
sir.
we are not supposed to lose even one second or 1 minute extra.
Understand, sir. Understand, sir. Understand.
And our motto is clear, sir, not just organizing this FDP. We want to contribute in the scientific community so that awareness can be spread out. What are the current trends, and
Yes,
so that's why we make it computer and electronics so that maximum number of people can be benefited.
correct, sir. Thank you, sir. Thank you, sir.
Thank you.
So,
Thank you,
Prasad,
Pradeep sir. Thank you very much, Pradeep
Yes,
sir.
sir. Yes, sir.
Nice, sir. Thank you. Anybody? Or else,
All the participants, overall feedback is already shared in the WhatsApp group and Zoom chat also, and YouTube live even. I request all of you to fill by to the earliest, because it would be closer by 5 p.m. And those who all paid, please upload your screenshots so that we could cross verify and recheck. Many of them paid the fees, but they didn't fill the Google form for registration of offline certificate. So we have kept again. This would cover all the registration process. And I apologize on behalf of myself, because I have been continuously sending messages in WhatsApp to register or to attend the FDP, join the WhatsApp group, communicating continuously in order to, we don't want any one of you to miss the opportunity to learn something new as a part of our academics. And even we thank on behalf of our department, so that in the working hours you people have been attending the FDP. Thank you.
Thank you, Sultan.
Big thanks.
Big thanks to Sultan also. So, any participants, or else we can close the day.
Good evening, sir. Shivprasad sir, how are you, sir?
Fine,
Myself,
madam.
Gauri.
Fine, madam. Gauri, madam, tell me, madam.
Yes, sir.
We have reconnected. Tell me.
First of all, I must congratulate to all NSRIT ECE team for conducting such a wonderful FDP. When I saw the schedule of this FDP, just I wondered how the people have covered all the topics in these 3 days. But finally, you have done in a very well manner, sir.
Thank you.
And I very thankful to Sultan sir by posting the messages every time, just asking, fill the feedback. You should not apologize, sir, to all. You should not say like that. Thank you very much, sir. And all the best for your future endeavors. We are eagerly waiting to attend such FDPs. Thank you very much, sir.
Thank you. Thank you very much, madam.
Thank you, sir.
Anybody? As 2 more minutes, we can wrap up the session. FDP. Any feedback from the people, participants? After so many days, like in this region, we are organizing. We initially thought we'll get less response, but we got a very huge response for registration, and similarly, good number, it's more than 90 participations in a day. It is reached to 100 also. Hopefully, everybody enjoyed the sessions, all the sessions. If any thing wrongly happened, so please forgive us. Once again, I thank all the members, all the participants. We did to the maximum extent. Anybody, or else Virendra, you can close.
Yes, sir. Dear participant, this FDP was focusing on a broader side, like electronics and computer science engineering. We have searched for best resources for the topic. In future, NSRIT, Department of ECE, NSRIT Visakhapatnam is committed to conduct this type of events, and we are also planning a huge FDP just in the coming days, coming months, for maybe international FDP. And apart from this, we are also planning to provide some dedicated FDP or workshop for the fixed topic like that. Suppose you are going for machine learning. Nowadays, everybody means most of the students have learned Python, or faculty member also enjoying this new language, Python, instead of R, MATLAB, or like that. Not going to replace all these, but it's an additional one. Nowadays, students don't use Excel to plot the graph. They use directly Python. But we are not interested only in basic machine learning or Python. We want to implement it as an application, like we did in our FDP, dedicated for medical application. In the same way, VLSI, MAMS, machine learning, or plasmonics, nanomedicine, we want to conduct such a future also, which will be dedicated to one topic only, with prime dedication as well as directed and dedicated resources for that. So please stay tuned with the NSRIT updates. I hope you enjoyed this 3-day FDP, and okay, please, if I also request, as our host is requesting us, don't leave your WhatsApp group until or unless you receive the certificate, so that communication cannot be affected. And we will promise you that we will not put so many messages. Or for upcoming events, you can follow this group. This group will act as a mute group only for informative purposes. And if any error, anything happened from our side, then please forgive for that. And thanks a lot. Please don't leave the meeting before filling that overall feedback form. Thank you very much. Dhanyawadalu.
Thank you.
Sir, I am stopping recording.
Okay.
I am stopping the live streaming also.